Hello everyone. Lecture 27, the last lecture from Chapter 8 on magnetic resonance imaging. So we are going to review some things today, and then we are going to introduce some new things about safety and something called functional MRI. So what have we talked about in the last lectures? We have talked about how magnetic spins react to a magnetic field. We have talked about how all the magnetic spins interact together to give a net magnetization, and how you can do something with that net magnetization by applying radio frequency pulses. We have talked about how contrast is obtained during an MR image by picking different times, the TR times, the TE times, and because different tissues have different relaxation times, T1 and T2, a judicious choice of TR and TE allow one to bring out and measure those T1 and T2 times. So remember, what have I said all along? Imaging is not a picture of the body. It's a physics measurement. That's why this is medical physics. It's not photography. You are taking a measurement. I even asked you in ultrasound, what are you measuring? You are measuring the arrival time of an echo. And you plot that arrival time and the intensity of that echo versus time. That then, when put together in a certain way, forms an image. What were we doing in CT? Were you taking a picture? No. What are you measuring? You are measuring the attenuation of X-rays along a line of sight through a body. And in CT, you're measuring the X-ray attenuation in a given voxel. That's a physics measurement. In nuclear medicine, what were you measuring? You were measuring the amount of radioactivity in different places in the body, measuring that with a gamma camera. And then we do special tricks to make that radioactivity accumulate in certain places, particularly cancers, so they light up. And in MR, you are not taking a picture. You are making a measurement of a certain region of the body, a voxel, and you're measuring its T1 time and its T2 time. And those things happen to be different for different tissues. So that's the mechanism of contrast in an MR image. We talked about contrast. We talked about then how you localize that voxel within a human body. That's the entire point of the last lecture. We're going to go over that again today because it's confusing and oh so important. And then we're going to talk about a few things today, which is we're going to talk about, one, how can contrast be increased, right? Other than just the T1 and T2 times in the body, is there anything we can do to add contrast to it? And it turns out there is. We're going to talk about how functional MRI can actually start to allow us to see what's going on inside the human brain. And then we're going to talk about the safety of MR, because it doesn't use any ionizing radiation, so it's one of our safest imaging modalities, but there's a couple dangers one needs to be aware about. So hopefully you've been doing all your reading. Again, I'll repeat it probably every time, because I want you to be treating our online classes just like you treated it in class. You were very serious with that. Hopefully you're being serious now. Do the reading first. Try to understand as much as you can, and then when you hear me talk about it and watch the PowerPoints with me, it's going to make so much more sense. I think if you're not doing the reading and just thinking you're going to come and listen to me talk and watch these PowerPoints, it's not going to do it for you. There's not enough detail in there for you to learn something new. You're learning it new from the reading. And then these things are like, oh, now I get what she was talking about. Maybe it's presented in a different way, different pictures, me talking, different animations. These are the way people can learn. You need to be accessing all of these learning modalities. You're reading, you're listening, you're watching. All of them together is enough to enable you to acquire new information. But relying on any one of them, particularly now that you're out of all your classes, it's just not going to be enough. So rely on all these different ways of thinking, okay? All right, so let's start, as we always do, with our most favorite part, the multiple choice quizzes. So these are going to be great. As always, I'm just doing this just to test your knowledge and for you to test yourself as to, did I pick up the things coming out of this lecture that I should have? So let's start. All right. Definitely we're going to talk about blood today. All right, we're going to talk about contrast agents, things that change or increase contrast in the human body. You read Kane, you read Hobby. What did either of them and or both say about blood being used as a contrast agent in an MRI image? Now there may be more than one of these here. So take a look at these and think about them. As always, I'm going to pause here, and then after you've written down your choices, unpause, and let's take a look at the answers. So go ahead and pause now. Okay, welcome back. So you're looking at these. Which of these did you think it was? It's more than one. As a matter of fact, I'm going to do what we usually do in class. I'm going to give you, before I show the answers, I'm going to give you another chance to answer these. Look at what your answers are, and what if I told you that there are actually 4 correct answers? So I'm actually looking for 4. Do you have 4 written down? If you don't, let's start over. So again, take a pause. See if you can figure out which of these 4 it actually is. I'll pause now. Okay, so welcome back. So I told you that there were 4 correct answers to these. Which 4 do you think it was? Let's take a look. Yeah, 1, 2, 4, and 5. And we're going to see some of these in our animations today. For sure, we're exciting all the spins in a slice. That was the whole point of the slice selection gradient. And the blood, because it moves spins out of the slice, reduces the intensity. So that's called washout. But we also, in 2 lectures ago, this is starting to get complicated, we talked about this thing called spin saturation, where once you bang some spins over, they don't respond well if you try and bang it again, so it'll make the target dark. But if you bang those spins over, but then they get carried out of the slice by the blood, when you come by another pi/2 pulse, those fresh spins are all ready to go. And so the blood can actually be brighter now. So flow-related enhancement. So it's not even a question of like, well, blood makes it dark, blood makes it light. It can be either, depending on how you use it. Number 4 was also mentioned. This is actually a very common contrast mechanism. We're actually going to give you an injection, right? Actually, they put you in the MR unit and they hook you up to an IV intravenous, and they put in a gadolinium contrast agent. It just goes into a saline type solution, and they flow it through you. And gadolinium is a magnetic molecule. And when they do that, it's going to affect the local magnetic properties near where the blood is, and that's going to change the contrast of that. And then lastly, it turns out that you don't even have to inject stuff because your blood has a magnetic agent in it right away, and that's called hemoglobin, right? We've talked about that. We talked about the optical properties of oxy and deoxyhemoglobin. Turns out that because think about it, and you guys know this from your intro biology classes. What does hemoglobin do? It carries oxygen through the body, but hemoglobin has iron in it. All right, so it allows, it affects the oxygenation state affects the amount of iron in the molecule, and that affects its magnetic properties. So whether the hemoglobin molecule is deformed because it's carrying oxygen, or it's deformed in a different way because it's deoxygenated, changes the structure of that molecule, right? Iron deficiencies are common in people with blood problems, so blood and iron are very closely related. Iron is ferromagnetic, it's got a magnetic property, so those 2 structures of the hemoglobin molecule actually have different relaxation times. And so we're going to be able to tell blood that's been oxygenated or deoxygenated in our MR measurement, which is really clever. So all 4 of those are true. Take a look at the next question. Functional MRI is called fMRI. That's the title of the lecture, so I hope you know that by now. What specifically is being measured when you do fMRI of the brain? There may be more than one correct answer here. So go ahead and take a look at that. As always, pause it now and write down your answers, and then when you think you're ready to hear the answers, unpause it and we'll resume. I'll wait, pause now. Okay, so you're back. Hopefully you've had a chance to take a look at these. Hopefully you've written down your answers. What did you think is going on during MR? How many of these things are true? Well, it turns out that there's 2 that are true. Certainly fMR of the brain is measuring the pattern and degree of brain activity during simple mental tasks. All right, that's all that we're doing. fMR is by doing simple things, thinking simple things, different parts of the brain will light up showing increased or decreased metabolic activity. That's what we can measure. How can you tell whether there's increased or decreased metabolic activity? Well, we're looking for the uptake of oxygenated blood. Again, there's a physiologic argument for this. If you are, just like when you're working really hard, work out in the gym, your muscles get starved of oxygen, starved of blood, and they start to get weak. When you're thinking very hard, different parts of your brain the metabolic activity increases. You need more oxygenated blood to flow into those regions because that part of the brain is actually working hard, and the MR is going to pick up the increased metabolic activity because oxygenated blood has a different signature in MR from deoxygenated blood. Why are 3, 4, and 5 not correct? Always, as you're going through these, be thinking, why are the wrong answers wrong? It's not just why are the right answers right. Why are your wrong answers wrong? The exceedingly slight variations in proton density observed in different parts of the brain. No, there is different proton densities for sure. And when you do a proton density map of the brain, you can measure these proton density variations, but that's not functional MRI. The decrease in magnetization relaxation time due to brain electrical activity. No, there's no electrical activity going on here. It's purely metabolic activity caused by the oxygenation state of the blood that your brain is using. The slight change in resonance frequency due to the proton chemical shift in regions with higher concentration. Well, that sounds like it could be right, but no, that's actually not true. There might be a very, very slight chemical shift, but we can't measure it in MR. So we're just purely looking at the magnetic properties that change, all right, due to the use of blood. So where are we going to start today? Well, again, because it's so important, I really want to review what we talked about in lecture 26 because it is one of the most complicated subjects that we're talking about. So I'm just going to go over and re-review how we spatially locate signals in the body. All right, and I want to talk about pulse sequences. So here are 3 different rows of a pulse sequence. I just want to show you different pictures of pulse sequences because in all the books that I've used for teaching medical imaging and teaching MR, they're always shown in different ways. You need to be familiar with all of them because they all are conveying the same information. And I need these words to not be foreign to you. I need you to understand what they mean. So we talked about 3 types of gradients. In a pulse sequence, there's a thing called an SS. What does SS stand for? Can you say it out loud right now? I can't hear you, so go ahead and do it. Slice selection gradient. All right, here's the patient laying here. In this case, the slice is an axial slice, right, cutting through the body this way. How does that work? I apply a magnetic field gradient, so it's weaker at one end, stronger at the other, across the patient from toe to head. When that happens, it means you beam in a radio frequency pulse of a certain frequency right here. That frequency is only on resonance when it matches the condition of a certain magnetic field, and then only that slice is excited. Because that's how that mechanism works when you look at a pulse sequence like this. When that pi/2 pulse, and I even said in the previous lecture that when you draw a pulse sequence, you really should indicate whether that's pi/2 or pi. So I like in this figure from Hobby that Hobby's actually doing that. Here's a pi/2 pulse. When the pi/2 pulse, which you beam in, is on, you have to have the slice selection gradient on, right? Because you only want that slice to respond. The rest of the body does not know that RF pulse is there. It just ignores it altogether. There's only one slice that's on resonance with the frequency of your radio frequency wave. You've determined it by setting that gradient. So the pi/2 pulse is on, the slice selection gradient is on. After all those spins in that plane have flipped, you turn off the slice selection gradient and you're done. All right, that's it. Now, we are looking for, this is the free induction signal right here. We don't want to measure that. We're waiting for the echo, right? The echo comes what? At what time? What time does the echo come after the pi/2 pulse? Say it out loud. You're alone. You won't embarrass anybody. Yeah, it's time TE, the echo time. All right, so we apply a pi pulse at TE/2, and then we wait another TE/2, and then we're going to have the echo. Right, so TE/2 is the time between the pi/2 pulse and the pi pulse. You wait another TE/2, so TE/2 plus TE/2 is time TE. Here comes your echo at a time TE after the free induction signal. What was our rule? Anytime you're beaming RF into the patient, you have to have your slice selection gradient on because you only want to talk to that one slice. All right, so this is a very simple pulse sequence. It's only got 1, 2, 3 lines because it's all that we're really showing here. But you can understand what all of these signals are. I mean, really, it's tricky, but it's not that complicated if you understand what we're talking about. So in this kind of 3-step pulse sequence, I really need you to understand what each row is showing and why the things are where they are. And in this case, as Hobby says, the echo after the pi pulse is from the entire slice. Look, I have it underlined. So the echo after the pi pulse is from the entire slice. Why is that? Because you have not implied a phase encode gradient or a frequency encode gradient, which will allow you to tell anterior to posterior or left to right. All right. So definitely the whole slice will respond, but there's not going to be any other information there. But that's how you build up the knowledge, right? Understand one thing. Do you really get it? If yes, we'll move on, and then we'll add another gradient. Do you get that? We'll move on. We'll add another gradient. So let's try doing that now. Let me go full screen. All right. So now 2 pulse sequences, SS, slice selection, plus FE. What does FE stand for? Say it out loud. Frequency encode gradient, right? So now I've just added this line. So we have what we saw before. So the frequency encode gradient in this case is going to be going from left to right on the patient. So it's a little weaker over here, stronger over here. Magnetic field always pointing in the same direction. The magnetic field never curves around. Never is a magnetic field pointing left to right, up, down, anything. Magnetic field always points in the direction of the main field. All the gradient fields point that way. So here is our slice selection pulse sequence, pi by 2 and pi. We saw this before, free induction signal echo. Now we've added another line. So this is, I call it FE. They're calling it G for gradient in Z and GX for gradient in X. I call it RF because that's you beaming stuff in, slice selection, and then frequency encode. The frequency encode gradient must be on during readout. We talked about this last time, right? So now you're reading out one particular row through that patient, right? You're reading out one particular row, and to do that, to read out across that row from left to right, this frequency encode gradient has to be on during the readout, during the time of the echo. So you determine the echo time by when you apply your pi pulse. So this will give you whether you're doing a T1 or T2 weighting. And then when you know that echo time is coming, you know when it's coming, turn on the frequency encode gradient. And that allows you to measure across the body, and that gets you one more of the spatial dimensions. Again, in the previous slide, we saw that if this frequency encode gradient is not on, you're just getting data from the entire slice. With the frequency encode gradient, it'll allow you to tell left from right in one row of that slice. And that was one of our rules. When you're getting signal readout, frequency encode gradient is on. Okay, so that's 2 of the 3 gradients you need. So the frequency encode, the slice tells you what slice you're in. Frequency encode gradient will read out one particular row, the whole row, during an MR measurement. And then the obvious question is, well, how do you know which row you're in, right? In this picture I'm showing here, you're like 1, 2, 3 from the top. How did you know you were in that particular row and not a row at the front of the patient and not a row at the back of the patient? How do you know? Well, that's, of course, the purpose of the 3rd gradient. The phase encode gradient will tell you which row are you reading. So I have to add this 3rd gradient slice. So this is, again, a full pulse sequence. RF you beam in, slice selection gradient, which determines which slice you're actually reading, frequency encode gradient, which is on at the time of the readout, which will measure across the slice, and then your phase encode gradient, which will tell you which row you're choosing. So the phase encode gradient in this case is going to be from anterior to posterior, which is front to back. A little weaker down here, a little stronger up here. It comes before the echo. It comes a little bit before the pi pulse as well. And its symbol, which we talked about last time, is represented by this ladder. The ladder means that we're going to go through and cycle through this pulse sequence. So in this case, this was an 8 by 8 slice. We need to do this 8 times. And each time we go through, we will use a different intensity of phase encode gradient. And that will tell you which row you're reading out. This thing determines which row you're reading, and then when you get to the frequency encode gradient and the signal, that reads across and you get that data. So this is the gradient ladder, repeated every time with different strengths. And so what I'm showing you is this. Say the gradient is really, really strong in the positive y direction. That means it would be strong up here and weak down here. Well, that determines you're in this row right there. That's one measurement. Repeat, go all the way back to the beginning. You have to wait amount of time. What determines how much time you wait? TR. TR is the repetition time. It's the time between your next pi/2 pulse and you start all over again. The second time you do it, you apply a different gradient. It's a little weaker up here, maybe a little stronger down here. That determines a different row. You read all that out, get your measurements, repeat. Go back to the beginning. You start all over. You wait, and you keep waiting time TR, TR, TR. This is a little weaker yet. That determines a different row. A little weaker yet. That determines another row. All right, and so on and so on. So does that make sense? Each time the phase encode gradient is a little bit different intensity, reads out a different row. If you want to do 8 different rows, you've got to repeat this sequence 8 different times. So yeah, MR measurements take a little bit of time, but of course the computer handles all of this, and we know that the time for TR is a second or so. So you're doing many, many of these measurements per minute, and that's how these MR measurements can kind of come in. All right. So I'll come back on the screen here so you can see what I'm talking about. So there are 2 main types of pulse sequences. Actually, there's tons of pulse sequences in MR, and the MR people spend a lot of time thinking about this. For the level of knowledge that you guys need to have, there's only 2 main types that you need to know, and we call them SE for spin echo, GE for gradient echo. SE is what we've been talking about all the time, up till now. A 180-degree pi pulse at time TE/2 causes a rephasing echo at time TE. This statement right here, this should make complete sense to you now. We've been talking about it for 3 lectures in a row. So the spin echo pulse sequence has to make sense to you. All right, so we've been talking about it. This thing here, this is a spin echo pulse sequence. You have a 180-degree pi pulse at TE/2 causes an echo at time TE. All right, so you should know that. That should be very clear. You probably think that's the only way to do it. It turns out that there is one little trick. So the other type, if one main type is spin echo, then the other main type is gradient echo. So spin echo or SE, gradient echo or GE. In a GE measurement, a very short magnetic field gradient applied in the phase encode direction can cause the rephasing echo. So it's still an echo. That's why spin echo, gradient echo. But gradient echo, the name tells you what it is. It's an echo caused by a gradient field, but not one of these long gradient fields, just a blip. We're going to hit the person with a pulse of magnetic gradient. We'll turn on these magnetic fields really quickly, and then that's going to cause an echo to happen. Usually, we do a lot of them to generate a train of echoes, right? And they're going to be separated by a time TE, and that's all going to be within one single 90-degree excitation. So let's go ahead and see what that looks like. Got an animation here that looks a little better, okay? This is a gradient echo pulse sequence. This is called EPI, so it's actually echoplanar imaging. And the reason we're talking about that, and we have to do that in this lecture, is we have to understand how fMRI works. All right, let me tell you just quickly, why are we talking about this? Because as I said, if you understood what we were talking about before, I said you have to do many, many, many of these measurements. You're waiting at time TR, even in the simple case we showed. 8 different rows. If you're waiting at least 1 time TR between each row, you're doing 8 of them. If you're waiting 3 TR, for example, so that's like 3, 4, 5 seconds times 8, maybe you got 30, 40 seconds for the whole slice. How are you going to measure brain activity if it takes you 30 seconds? It's not possible. If you're trying to measure your brain lighting up because you're thinking about something or doing something, we need a measurement in like milliseconds. This is way too slow. So how can we make this sequence really, really fast? That's going to be the point of the EPI, echoplanar imaging. So how does that work? Here's your pulse sequence again. RF, slice selection, phase encode, frequency encode, signal. I always have these 5 rows. So when you see a pulse sequence, you need to be familiar with these 5 rows. Gradient echo, what's the one thing that makes it different? No pi pulse. right? So in a gradient echo pulse sequence, you look at the RF, you're putting in a pi by 2, there's no pi pulses anywhere. If I just showed you this, and I asked you, is this an SE or a GE pulse sequence, what would your answer be? You know the answer. An SE sequence has a pi pulse to generate an echo. There are no pi pulses. This cannot be an SE sequence. Instead, what we do is we apply a phase encode gradient. See this little blip? And it's applied at some time, and then here comes the echo at time t over 2. So this is a phase encode gradient right here. Let's go back. It's going to cause an echo here. You apply another phase encode gradient here, you get an echo here. Another phase encode gradient here, you get an echo here. Another phase encode gradient here, you get an echo here. So this is blips of phase encode gradient separated by time TE. So it's TE from here to here. It's TE from here to here, which means you have echoes separated by TE from here to here, TE from here to here. And so you do this. Let's just let this thing play. Blip, read out a row. Blip, read out a row the other way. Blip, read out a row the other way. So look at what's happening up here. See how before you were resetting the experiment every time and starting from left to right? This is just going to move you through the whole slice very, very quickly. So let me rerun that animation again. So watch for the yellow blips here, which indicate when you're pulsing a magnetic field gradient, and that'll cause this row to be selected. As soon as that row gets selected, you turn on the frequency encode gradient, because this must be on during readout of the echo. Then as soon as you get to the other row, do you wait and then apply another pi by 2 pulse? No, just hit it with a blip right away, move to a different row, and read it coming back the other direction. Watch this again. Blip, read out the row. Blip, new row, read out. 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 Right? As long as your frequency encode gradient is on at the time you expect the echo to come, you're going to get these measurements. And these phase encode gradients just step you through that slice. You can do this all in one excitation. All right? So that's the advantage. One TR excitation, one pi by 2 pulse, spin flip, gets you all of that measurement all at once. All right? So that is the epi sequence. So echoplanar imaging. So you need to know some of these names. What is an echoplanar image pulse sequence? It's just a series. When you see a series of very short phase encode gradients causing echoes, that's an epi sequence. And what does that get you? Why would you do that? One simple answer. So if anybody ever asks you, why would you use an EPI pulse sequence? Answer very simple. Speed. Speed, pure and simple. It's so fast. The whole slice is acquired in one excitation of the spin flip, less than 100 milliseconds. The whole slice, really fast. And we're going to need that if we want to do fMRI, functional MRI. So let's talk about functional MRI, because these are the types of images that we want. For functional MRI, we want to have the patient doing or saying or thinking something, simple mental tasks, we said, and then we're going to see which parts of the brain light up in our MR image. So most of functional MRI, and we're going to see a video of this in just a second, is based on this idea called BOLD, the BOLD contrast principle. Blood, oxygenation, level dependent. B-O-L-D, BOLD. All right, so different parts of the brain are going to light up because the amount of signal is dependent on the blood oxygenation level. Because areas of the brain that are working hard and are thinking hard require more oxygenated blood to support their metabolic activity. So that's how we can, doctors and physiologists and psychologists, psychiatrists can start to map out what parts of the brain are actually active when you're doing different tasks. So let's go ahead and take a look at how this is actually done. So there's a link embedded in this PowerPoint. So functional MR of the brain. So it looks like this. So functional MRI, which we call fMRI, indirect method of brain activity, all right? So watch what's going to happen in this animation, because it turns out that the amount of oxygenation in the blood is not real big. So we need to tie it to something. So in this simple experiment, we are asking the patient, say they're going to be looking at a light or listening to some headphones, and we're going to ask them, could you please move your thumb in response to, say you got a small, they wear sometimes glasses or they wear headphones. So say you give them a small pair of glasses and they say, when you see the little red light come on in the corner of your glasses, move your thumb. When it goes off, you stop moving. And we're going to need him to do this for like several minutes at a time. Watch what happens. Wiggle your thumb, wiggle your thumb, wiggle your thumb, stop. Wiggle your thumb, wiggle your thumb, wiggle your thumb, wiggle your thumb, stop. Light comes on. Right? So the patient is responding to some external stimulus and doing it many, 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 many times in a row. The data you could see in that image is really lousy. Okay, we're not really good at getting MR signals out of the brain yet. These come in very fast. They're very weak. If you just said, can I see what parts of the brain light up, it's much more complicated than that because the change in signal is really small. So what we can do, though, is we know when we were telling the patient to activate and deactivate, activate and deactivate. And now this could be wiggle your thumb, don't wiggle. Wiggle your thumb, don't wiggle. Wiggle your toe, don't wiggle. Wiggle your toe, don't wiggle. It can be think about your favorite song. Think about a cat. Think about your favorite song. Think about a cat. It just has to be something where you do it over and over and we know what the pattern is. And then we look at the data coming out of your brain, which is noisy, but we superimpose it with the periodicity that we know is happening that we asked you to do. And then we see how those things line up. And then you can tell which areas of the brain are responding in sequence with the stimulus that you've given them, and which parts of the brain don't do anything in regards to that sequence. All right, so you have to do this. So there's no way I can say, like, think about wiggling your thumb and get a measurement. This actually does take minutes. So although we use these super fast pulse sequences, I think they have to, like, do these things for like 5 minutes at a time to get enough data of on, off, on, off, on, off. But eventually, you can map up the stimulus that you know with the timing of whatever is going on in the brain, and you can get a relationship, and you can kind of start to tell where in the brain these things are occurring. And that's called functional MRI. That's how it works. It's a really, really super cool tool. Okay? So functional MRI, so here's this view graph, which you should now remember from that animation we just saw. And it's kind of got poor, so here's an actual MR image with the physiology, and then on top of that you superimpose these BOLD, blood oxygenation level areas that seem to be lighting up. One of the most interesting things we can do is some students and I went up to a conference in Western there. They have a very great scientist that they just stole from Cambridge, I think, several number of years ago. He's a famous guy because he had published this very famous Nature article. And he was doing these studies. He's on BBC. This was really fascinating, which is via functional MR, they were actually able to communicate with patients who are in a coma. Doctors refer to coma sometimes as a persistent vegetative state, right? So these would be people who are completely non-responsive, lying in hospital beds. You know, they're alive, but they're in no way able to communicate with patients. And the prevailing wisdom in medicine for a century has been people in persistent vegetative state they're not aware of their surroundings. They don't feel pain or discomfort. You know, they're brain dead, right, if we call it that. So they were able to hook up, take a number of patients, about 8 patients, and put them in an MR scanner. And they wanted to see if they could communicate with the patients, even though they're completely nonverbal. But they can see what's going on inside their brain. So what they told the person to do is they would ask them very simple questions. And they say, if you want to answer yes, you have to think about swinging a tennis racket. And this is what's so amazing about brain, the way the brain works, is when whatever's going on inside your brain, when you swing a tennis racket, this is well known that the brain actually activates, 100 milliseconds before the muscles actually respond. When you have a thought to move, the brain perceives that thought and imagines you swinging the racket, and then that sends electrical signals to your spine, which then controls your nerves, which then make the muscles respond. Turns out, because the brain stuff comes before the spinal cord stuff, it doesn't matter if you're paralyzed and can't swing the thing at all. The brain lights up in exactly the same way because the brain is what's issuing the command to the rest of the body. So if you just right now close your eyes and think about you swinging a tennis racket as hard as you can, that part of the brain that is ordering your body to do the tennis racket fires. And we can measure that with functional MRI. That's cool. But it gets cooler, because now you need to distinguish yes from no in a yes or no question. So they told the patients, if you want to answer no, imagine yourself navigating through your house. So again, you guys do this right now. Close your eyes and imagine picture yourself swinging a tennis racket on a tennis court as hard as you can. It's a very physical activity, all right? It uses a certain part of your body. But now close your eyes and imagine you wake up in the middle of the night and you get out of bed, and in the dark, you have to navigate from your bed to the bathroom and back without stubbing your toe. How would you do that? How do you navigate where the doors are, where that dresser table is? All right? That uses a completely different part of the brain. But again, as you think about navigating through the house, that is equivalent to your body doing the navigation. It's just the fact that it doesn't happen does not matter. The brain is giving those orders. And you're using a kind of spatial location sensory part of the brain. It's a different part of the brain completely than what controls muscle firing. And you can see that in the image right here. When the person is thinking yes, for thinking about tennis, a certain part of the brain lights up. When the person thinks no, they want to answer no, then they think about navigating through the house, and a different part of the brain lights up. So the point is, even someone who's in a persistent vegetative state, you can't ask them to say yes or no. They can't control their body, and you don't even know if they're able to hear you. So they put these people in the MR scanners, and they worked with them for days and days and days. And shockingly, this is what this guy, as we were listening to him talk at Western, our audience of students and physicists, we were just completely amazed. I think it was something like 50% of the patients could actually reliably respond. And these were patients that all of the doctors said were persistently vegetative and were in no way aware of their surroundings. It turns out they could actually communicate with the people. And this was amazing, right? Because it's a whole new insight. So people who had long been in these states and completely unable to communicate with the outside world were now able to communicate. The interesting things is this story it's really a good news kind of story, and really interesting that for most of these patients, this was not a bad situation to be in. I think one of the early things they asked them, is, are you in pain? Are you uncomfortable? Is this unbearable? And the answer for the most part was really no. But they know this was not random firing of the brain, because they would start off with a very simple question. They would put a patient named Brian, into the MR, for example, and the yes or no question would be, is your name Brian? Is your name Brian? Is your name Brian? And then, is your name Tom? Is your name Tom? Is your name Tom? So if it's just random firings of the brains, because you could imagine that it's just randomly responding to some question. But if your name is Brian and the person knows it, it should always be no for is your name Tom? Is your name Tom? And it worked. And so we're able to get into that. So what this guy is trying to do now, if you can do that in a full-fledged MR machine, why couldn't you do that in a small MR unit that you can wear? This is what he's working on. So like our Dr. Zhao is working on MR miniaturization. This guy is working on like wearable MR. So instead of having to put people with brain injuries or body injuries into a scanner to do this, maybe they could wear a helmet where the MR is actually starting to pick up their thoughts, and then of course this yes or no can be commuted to some sort of external voice. Now people who are in comas can actually start to talk. I think that's coming in the future. Medical physics. Super cool stuff, right? You got to admit that that's cool. All right, so that's functional MR. Let's talk about blood flow contrast. All right, so we talked about what are the different ways that blood can be used as a contrast agent. So one of the ways is going to be outflow or washout. So I'm going to show you this animation, but what's the point? So let me explain the animation that's coming first. Here's a slice of the body. There's a blood vessel flowing through it. So when we look at the slice looking down, we should see the blood vessel in the middle of it. And we're going to see two different ways that make this big aorta blood vessel dark or make it light. If it's dark, we've had washout of spin. So let's just see how that works. All right, so this is again from our IMAIS site, which I'm using all the time. You guys should too. Vessel signals and spin echo sequences, right? So just read along with me. All right, vessels generally appear as hyposignals. What does hypo mean? Hypo means lower reduced signals. Hyper would be a extra big signal, or white. Hypo is an extra weak signal, or black. So vessels are hypo, or black, in spin echo sequences due to the outflow effect. The spins in the slice are excited during the slice selection pulse, which is usually a pi/2 pulse, just like everything else. You wait a time TE/2 when you apply the pi pulse, but guess what? By the time you've waited TE/2, all those cells in the blood that were excited have now flown out of that slice. So they cannot respond. They're not in the slice anymore. They're not going to be on resonance. So, and that signal will get lower the faster the blood velocity is, right? The quicker they're moving out of that slice and the darker it'll get. So not only will it get darker, but how dark it gets tells you kind of how fast that blood is actually moving. And there's a complete signal void, completely black, if all the spins have moved out of the slice. Let's take a look at what that looks like. Okay, here they are moving. There's the slice. Everything's excited. Now look, your waiting time T over. See how it's moving up with it? Now you apply your pi pulse. Wait for the echo to come in. And there's your data. All right? When you excited it, I'll show it again. When you excited it, everything got excited. But then you have to wait a time TE/2 and another time TE/2 to hear the echo. By the time it took you to wait TE/2, which you chose, those spins which are excited have moved out of the slice. So when you apply that pi pulse, nothing happens in the middle. And so they do not rephase, and you do not get an MR signal. Watch this once again. So this is the outflow effect. All right, so I hope that makes some sense. All right, so a vessel with flowing blood will carry the excited spins out of the axial slice that you've selected, and that'll lead to a reduced signal, outflow or washout. I hope you can understand that. But I hope you're not sitting there thinking, okay, I get it. Blood flow always makes, a vessel in an image appear dark because of outflow. Not true. I can also make it appear bright. And this is something called TOF-MRA. It's using actually an inflow effect. So TOF-MRA is time of flight, magnetic resonance angiography. Right? So angiography is measuring these blood vessels. Let me zoom in on this picture. Look at these beautiful images. These look like some of the angiograms from X-ray CT, but these are actually MR images. Right? Beautiful images of the blood vessels due to this time of flight magnetic resonance angiography. And for this effect, it's all going to be based on spin saturation. So you have to think back a couple lectures. We talked about spin saturation. So what happens when you start off your experiment, the pi/2 pulse bangs them over. You wait some time TR for the spins to recover, bang them over again. And we said if you don't wait long enough, bang, and they start to recover, and then you hit it with another pi/2 pulse, nothing happens. They have to be fully recovered to get that spin flip. If they have not recovered all the way, we call that spin saturation. All right, usually it's bad, but in this case, it's good, because what we're going to do is take the whole slice, bang them over, we start to recover, and then we're going to bang again. What happens? Nothing, because they're saturated. The arrow will be black. Aha, except for what? There's going to be an area in the blood vessel where those spins that were saturated have flown out. The fresh blood coming in has no idea that there's an MR experiment going on. So when you combine with that second pi/2 pulse, the only thing that responds is that fresh blood that's moved in. And it responds great. The spins in the blood vessel are like, hey, time for an MR experiment. Boom, they do that. Then you can do your whole experiment with a nice bright signal. Everything else will just be dark. That's why in these images that I'm showing on the screen here, the blood vessels will appear bright because they're the only spins that are responding. Everything else appears dark. So let's take a look at how that works. I'll go back. Time of flight MR angiography. All right. So we are going to saturate the stationary signal with a very short TR. Right. So very short TR means bang, 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 bang. Right? If you apply like whatever T1 is, so you go to a very short TR time where you're just hitting it with pi by 2 pulses, bang, 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 bang. Each time you do that, fewer and fewer spins can respond because they're all tipped over. They can't do anything anymore. So that's called spin saturation. Give it a couple pulses, bang, bang, bang. Nothing can respond. Very short TR. So the longitudinal magnetizations, it doesn't have time to relax. The signal goes away. But now fresh flowing blood that's coming in has not been saturated. Its longitudinal magnetization is maximal. It's the only thing that will respond. And so the signal from blood flow is stronger, hyper intense. A bright white signal. Let's take a look at that. Here's the animation. So look, right? So this signal here is bang, bang, bang. You're doing it fast, doing it fast, doing it fast, doing it fast, doing it fast. Everything else is just dark and gray. Let's look at that again. It just can't respond because you're saturating it. The signal comes in. The signal from the blood vessel is going to be bright because it's always fresh blood coming in. That fresh blood that has not been saturated, completely able to respond to the RF pi by 2 pulse you put in. And so that can make it very, very bright and white, and that's called angiography, right? So that is magnetic resonance angiography, MRA. All right, so that's what we're talking about here. Time of flight MR angiography, a very common technique in magnetic resonance imaging. So that works pretty good too. All right, so this is a way that blood can be used for contrast by making it a hyper-intense or hypo-intense signal. And we talked about another thing in the multiple choice question we had at the beginning, which was injecting a magnetic material into the body. So just like blood can make the signal bright or hyper-intense or dark hypo-intense, gadolinium can make the image bright hyper-intense or dark hypo-intense. That's what makes MR so complicated. You can't just memorize things. You need to think, oh, what would it do? So gadolinium is a paramagnetic molecule. It's an element. Just look, you might not have ever heard about it, but it's a very important element for modern electronics. You put it into a solution, inject it into the patient. It'll disturb the local magnetic field, which means that T2 star is reduced. Right? T2 star is this magnetic field inhomogeneities. There is a T2 star sequence that allows you to look at the different tissues depending on T2 star. Because it makes T2 star even smaller, that'll be a hypo-intense signal. Because the quicker the dephasing is, the more quickly everything goes away. So hypo-intense means darker. It's darker because it goes away more quickly. When you inject it into people, it also reduces T1 and T2 of the proton. So this is T1 time of hydrogen, T2 time of hydrogen is reduced. If you reduce T1 times, then when you do a T1 weighted sequence, the things that are bright are going to become brighter. Because remember, if that doesn't make sense, you have to go back to my PowerPoints, look at what that equation is. There's a 1 minus e to the negative TR over T1 in those terms. So when T1 gets long, your TR is just fixed. That means that the things that are recovering quickly are even brighter in that image. All right, so it is possible to get a brighter image. So here is showing the effect of contrast agent on images. This is a defect of the blood-brain barrier right here, shown in an MRI image. So T1 weighted, this is a T1 weighted image. In the left, let's make it big. In the left image, without contrast, it's here. Can you see it? Barely. You inject the contrast, which goes into the blood. Look at that. Look at the beautiful bleeding inside the brain revealed by the gadolinium push, they call it, right? You push the gadolinium. They do the measurement beforehand. They know when it's coming. The technician opens the IV. They push it into your body very quickly. It flows through the blood vessels. Now you have this beautiful blood-brain barrier after a stroke. So this is the stroke in a patient right there. Beautifully observed in gadolinium. It's a T1 weighted image. So wherever the gadolinium is, you get a hyper intense signal. It's brighter, it's whiter. All right? So I hope that makes some sense to you guys. If that doesn't make sense, write down your questions. We can talk about it during my office hours. Okay, and then the last issue that I want to talk about is safety. Because in general, what do we know about MR? Well, it's very, very safe. It's one of our safest imaging modalities. So I want to talk about two things with regards to safety. You know, you should be cognizant of those things. So I want to talk about one, safety due to magnetic fields, and two, safety due to the radio frequency fields you're beaming in. So let's do one first. Safety due to magnetic fields. As far as we know, these strong static fields, 1.5 Tesla, 3 Tesla, 4.5 Tesla, they have almost no physiologic effect on the body. You can be in these fields and lay there. They don't tend to do anything to you at all, as far as we know. There is one effect that is possible. So anyone who took first year physics, right, the 1410, knows about F equals V cross B. So do you remember that? There's a right-hand rule that if you have something flowing V and you, let's just do this way, V and curl into the direction of B tells you what direction of force on a charged particle is. It's called the Lorentz force law. F equals QV cross B. You know what? Let me write that down because you might not have seen it in a while. So it should be a vector thing. Hopefully you're writing it down with me at the same time so you know exactly what I'm talking about. But we're talking about this guy. This is the Lorentz force law. Force equals QV cross B. It's a cross product. It says that the force on anything with charge Q, fingers in the direction of V, curl into the direction of B, and your thumb shows which way it's pointing. Maybe let me do it this way. V curled into B tells you what the direction the force is. In this case, right at you. So that says that anything moving in the body can respond to a static magnetic field B. Well, when you're laying in an MR machine, you're not moving, are you? Is anything moving in your body? Yeah, your blood is. Your blood is flowing with velocity V. Is your blood charged? Yes, it is, because your blood carries all these ions, right? When you drink Gatorade, right, electrolytes and stuff, when you're depleted, you're drinking Gatorade to get these electrolytes, these electrolytically charged things, calcium ions, magnesium ions, sodium ions, back into your body. So your blood is carrying charged ions. They're flowing with some V, and so when you're in a main field, there is a force, and they know that this is true, that if you're in there long enough, you do get the accumulation on different sides of your blood vessels of different ions, right? Because if you're flowing this way and the field is down, you're going to get sucked to either side of a blood vessel. We don't think there's any physiologic damage to that, but it is known that there's some electrochemistry that can happen, but no one's ever really in a machine long enough for that to make a difference. So the strong static field has almost no effect. But what about these strong transient gradient fields? This is much more dangerous. So it's not B. So no, but it's the change of B. We call that dB dt. Yes. All right. So this is kind of how I think of the dangers due to magnetic fields. Is there a danger due to the magnetic field? No, not really. But when the magnetic field changes, dB dt, yes. And is the magnetic field changing? In the gradient fields, it is. All right, so when you guys if you've ever had to go into an MR, or if you ever see an MR, the patient is going to be wearing headphones like this. It's so the nurses can communicate with them, but also it's bloody loud. If you ever see these things, it's like bang, 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 bang. It sounds like somebody's hitting the side of the machine with a hammer, for real. It's really loud. That banging is these gradient fields. Slice selection, phase encode, frequency encode. The gradient is turning on, off, on, off. And when dB dt is large, it means you're trying to apply a huge magnetic field with the gradient coil, and you turn it off. On and off, and on and off. And every time that happens, that's a change of field. It's a change in flux. And when it's a change in flux, any metal loop does not like to have a change in flux, so it's responding to it. So that banging sound is actually the gradient coils trying to tear themselves out of the MR machine because you're forcing current through it and turning that field on, off, and these things hate that. So there's actually a huge amount of force on all these gradient coils because they just don't want that field coming on, off, on, off. And the idea is of flux is dB dt is a change in current, and when you put it through a loop of anything, then there's an induced current in there, and that induced current can be bad. So these dB dTs can interact with the body's electrochemistry. So some MR patients have experienced hallucinations, tastes, a tapping sound inside their brain, smells. And this is because it does interact with the electrochemistry, and your brain is mostly electrochemistry, so that's bad. As well, we worry about current loops, right? Because dB dt is huge, and that's the flux. And the amount of current induced in a loop depends on the flux. So if you have any loops of wire in the body, there's going to be a huge electrical current. So when they put on the headphones, like I'm wearing a pair of headphones right here, if it had a loop in it, just like this laying on my side, this thing would start to generate so much current induced through it that a patient can get burns. So no loops anywhere in the patient. In fact, I think they go so far as to say when the person's laying, they're not even supposed to cross their arms, because crossing their arms is basically a loop, and you get electricity flowing through this loop, and you can actually get burns to yourself. So that's not so bad. So that was that. What other dangers do the magnetic field? Well, there's the missile effect. Okay. I'm sorry we don't get to go to the MR imaging suite. We seem to have missed out on a lot this semester. If we had seen the MR imaging suite, we'd see that everything in there has to be non-magnetic. MR is really expensive for a couple reasons, and one of them is anything which goes into that room that's magnetic becomes a projectile, and it'll suck you into that bore and damage the patient. So everything that goes in there, all the equipment, the IVs, the EEGs, every piece of equipment that the nurses are carrying has to be completely non-magnetic, which means you have to buy it special, which means it's expensive. If a patient goes in there and does not tell them that they have a pacemaker, the field is strong enough where it could tear the pacemaker out of the patient and kill them. It's a big issue. I think when we talk to the nurses, they're quite, and the technicians, they're quite interesting to talk to. Most of their job is just asking the patient over and over, do you have anything magnetic? Anything magnetic? Implants. I mean, it could rip it. A magnetic implant could be ripped right out of your bone if the field is that strong. Tattoos can actually respond. Not all, but some patients, because they use for the red colors, there's iron particles in the red dyes of a tattoo. Those tattoos can start to heat up and start to burn, and the patient has to come out of the MR if they're feeling uncomfortable. It's that strong. So all this stuff needs to be known, and they're very carefully screening people when they come in that you don't come in with anything magnetic. So this is where you can have some fun. So if you're bored after this lecture, go online. Take a look at some of these videos. So here's a fun one. Let's kind of watch this together. See if I can bring myself up here. So fun with decommissioned MRs. We're just going to show what the danger is. All right. So this is a magnetic oxygen bottle. Many patients are on oxygen, and maybe you wouldn't be thinking about it. So they're going to show you how strong the magnetic field is. So here's the bore of the MR. They're going to put a watermelon in the bore, which simulates a patient head, which is kind of like a watermelon. And they're going to show how this thing can just get turned into a projectile. So the field is low here. They're just going to nudge it, but the field changes so quickly. Wham! Okay, well, that's a dead patient if you're not careful. You know, everything turns into projectile. Change, wrenches, surgical apparatus, scissors, anything that's magnetic, you wouldn't even know it. You come in, you won't be able to hold it, it'll get torn out of your hand into the bore of the MR. There's a bunch of videos on YouTube of stuff like this. It's quite funny. Now he's looking at the damage, and now he's going to try and pull the thing out of there. Good luck with that. You know, a human's not strong enough to do that. You're not going to be able to pull that thing out of the bore of an MR magnet. They're too strong. Way stronger than you think it's going to be. So here's the back side. So by the way, this was the head coil, right? So, and there's the watermelon, which would be a patient's skull. That would be bad. So This thing here was the head coil. So that's how we're talking about picking up RF waves, from the patient. This just goes right around the patient's head to get those antennas really, really close. All right. So, and then they finish, I don't know what year this was, apologies, boy 6 killed in freak MRI accident. A 6-year-old boy died during an MR in New York area. The powerful magnetic field jerked a metal oxygen tank across the room, crushing the head. And how sad is that? So it's real. So projectile hazards are real. Then we said that was 1 for all the magnetic fields. We said danger 2 is the RF. So you're beaming in radio frequency waves. That's like a microwave. Is that bad for a patient? Heating of tissues is possible, but of course it depends on the intensity of the duration of the radio frequency waves that you're beaming in. So it just has to be monitored. Just like we said with the ultrasound is in general safe, but if the ultrasound is cranked up too high and for too long, it can damage certain tissues due to heating. Same with these radio frequency waves. So the computer controls all this. It won't allow you to beam enough RF radiation into the body, to do that. So the RF we don't worry about too much. You can't have any metal objects on you. Think of a microwave again, right? So you guys have all heated up cups of coffee in the microwave. No problem. What do they always say? Don't put a spoon in the microwave. Don't put aluminum foil in the microwave. It starts sparking and it goes crazy. Well, that could happen if you have metal inside the MR as well. That's just from the RF that you're beaming in. So it kind of turns it into a miniature microwave. So that's not good. But essentially, MR is, along with ultrasound, I would say our safest imaging modality. Nuclear medicine, you have to put radionuclides into the patient. That's not so great. X-ray CT, beautiful detail, but ionizing radiation is bad. MR and ultrasound, essentially completely safe. No radiation, no radioactivity. The only problem is, like I said, currently a scan right now takes about 15 to 30 minutes in that range. The time it takes the technicians to get you in, get you laying on that bed, get you into the thing, get some pre-scans and get the data, 15 to 20 minutes. And these machines cost about $3 million. That might be just for the machine. The whole suite to go around it, all demagnetized, all the special equipment, millions and millions of dollars. So the only problem is right now it's expensive. So we would like to miniaturize that. So again, our own Dr. Zhao in the department has some big plans for making miniature MRs that can be much smaller, more portable, more cheaper, bringing it to the masses. So that could be cool. Okay, I think that's about enough for this lecture. So this concludes our chapter on magnetic resonance imaging. All of this material, it will be on the exam in one way or another. You've got your homeworks. Be working on those. Get your homework questions done. Review all of this material. And some of 5, so stuff for the exam will be Chapter 5 on X-rays, Chapter 6 on nuclear medicine, and Chapter 8 on some of this bit of MR. So if you have any questions to that, please write them down. Get in touch with me during office hours and hope we can straighten them out. All right, everybody. Enjoy that, and I will be talking with you shortly. Good luck.